talk about the fundamental theorem of calculus, which probably is obviously a pretty important one because there's the word fundamental in it. And the fundamental theorem of calculus is really going to form really what we do for the rest of the year. So it's an important one. Make sure you take careful notes on this, and especially write down the theorem itself. So let's get into it. So the first thing we're going to do is we're going to define kind of a new function in a new way that we haven't seen before. And what we're going to do is we're going to use an integral to actually define a function. So we have this function right here. And it looks like it's just a few different line segments, each with a slope of either -2 or +2. And what we're going to do is we're going to say capital F, this is kind of convention for fundamental theorem, capital F of x is equal to the integral, we're going to say from 0 to x of, let's call this guy here little f of x. So integral from 0 to x of little f of t dt. Okay. So what this means is that for any value of x, we're going to integrate from 0 to that value, and that's going to give us our big F function. So let's just think about finding some values here. Like if we wanted to find capital F of 1, well, just like every other function we've ever done, whatever x is, we put it in where the x belongs. So f of 1 is going to be the integral from 0 to 1 of little f of t dt. Now, you might be confused with why we're using t's. And remember that this is a dummy variable. It doesn't matter what this variable is in here. If we integrate it, it's going to be the same thing. We're just finding the area under the curve. The reason we can't use an x is because if we had an x here, we'd have too many x's, right? Because then f of 1 would be integral 0 to 1 of f of 1, but that would be a constant. So we have to use some kind of a different letter in here to be able to define it this way. So let's find this value. So the integral from 0 to 1 is just going to be the area of this triangle right here. So the area of that triangle is 1/2 base times height. So 1/2 times the base, which is 1, times the height, which is 2. So that gives me an area, or a function value, of 1. So there's a +1 area in there. Okay, so I have f of 1 is 1. Let's do f of 2. Well, f of 2, I think we can use some symmetry to figure that out, because it's going to be these two triangles added together, or this one big triangle. That's going to be another +1. So it looks like f of 2, it's integral from 0 to 2, f of t dt. That's going to be 2. Let's do f of 3. Well, f of 3, let's see. So we have +1, +1. We know that integrals, when we have area underneath the curve, that the integral value then is actually going to be negative between 2 and 3. So from 0 to 3, we have +1, one more +1, and then this guy right here is actually giving me a -1. So f of 3, if we do our integral from 0 to 3 of f of t dt, that's going to end up being back down to 1. So now some of the tougher values, what if we wanted to do like f of -1? We'll do f of -1, we'll also do f of -2. So f of -1, that would be the integral from 0 to -1 of f of t dt. And remember from our integral properties, we don't love to go from a right value to a left value. So what I'm going to do is I'm going to use our integral property that says this is the opposite of the integral from -1 to 0 of f of t dt. Now that's as if I was going forwards, which I like better. So we know the area underneath here. So the integral from -1 to 0, that would be -1. But because we're going backwards, it's the opposite of that. So this is -1, which is +1. So f of -1 is +1 because we're going backwards and the area is underneath. So I'm going to change that actually to, well, let's leave it as a negative. That's probably better. We know the area is 1, so because it's below the graph, it's negative, but because we're going backwards, it ends up being +1. And then f of -2, same kind of idea. We got another -1 here, but because we're going backwards, it's going to be the opposite of the integral from -2 to 0, f of t dt. So that's going to be -2, which is +2. So now we kind of have an idea of just how to get these values, because this is kind of a weird defined function. But getting different values, we're just integrating from 0 to that value to get each of the function values. So now what we're going to do is we're actually going to plot some of these points and see what they look like. So here what we're going to do is we're going to plot capital F of x. So we're going to go back and forth a little bit. So remember, capital F of x, we call this an accumulation function because it's accumulating area from a point to whatever function value we want. So f of 1 is 1, so let's plot that. F of 1 is 1 right there. F of 2, I think, was 2. Yeah, that's what it looks like. And then f of 3 is 1. So f of 2 is 2. F of 3 is 1. F of negative 1, I think that was positive 1. Oop, too far. F of 3 is positive 1. F of negative 1 was positive 1. And f of negative 2 is positive 2. Let's think about f of 0. Do that one. Keep going the wrong way. F of 0 would be integral from 0 to 0 f of t dt. That was one of our integral properties. If we integrate from the same value to itself, that's always 0. So that means f of 0 is 0 right here. Now let's think about how we would connect this graph. Very rare that they ask you to make this graph, but I just kind of want to get a picture and talk about it. So between 0 and 1, this is not going to be a straight line. Because if you think about how we're actually accumulating area here, at the beginning we're accumulating area slowly, but then we end up accumulating faster and faster and faster because each one of these bars is going to get longer. So we have a curving graph coming from 0 to 1, kind of like that maybe. And now let's think about what happens between 1 and 2. Between 1 and 2, we're still accumulating positive area, but it's slowing down. We're still getting positive area, but it's slowing down because it's the opposite of what happened between 0 and 1. 0 and 1, we were getting longer lines. Now we're getting shorter and shorter and shorter lines. So it's going to be increasing still, but at a slower rate. So it's going to basically curve downwards like this. Looks like we might have an inflection point there at 1. And then between 2 and 3, what's going on is we're actually getting negative values. We're losing ground on f because we have these negative values going down. Okay, so what that means is going to go down like this. And on the left, it's pretty much the opposite. When we go left here, we are gaining more area. And because we're going right to left, even though it's below the graph, we have positive values. So that's going to be curved going upwards like this, something like that. And then if we continue going, we're going to actually be continuing to gain area, but it's going to be getting slower and slower and slower. So we're going to curve downwards like this. So now what I want to think about is, okay, if this is what f of x looks like, let's think about what the derivative of that graph would look like. So the derivative of this graph, well, let's plot our zeros first. It looks like there's a horizontal tangent at 0 and at 2. So let's plot those. It also looks like we have a horizontal tangent happening at negative 2, even though it's right at the edge of the graph there. And then it looks like we have increasing concave up at the beginning. So that means that we're going to have a positive derivative that also has a positive slope. So we have positive derivative with positive slope. So maybe something like this. It kind of looks like a part of a parabola. So maybe like a straight line up to 1 there. Maybe something like that. It looks like, yeah, that slope could be maybe 2. I believe that. And then between 1 and 2, still positive derivative values, but we're concave down now, so we'll have a negative slope. So something like that, maybe. And then between 2 and 3, we have decreasing, so it's going to be a negative derivative, and it's concave down, so it'll also still be sloped down. So it looks like that line kind of just continues. And then on the left side, right here we have decreasing graph, concave up, so it'll be negative derivative values, but with a positive slope. So something like this. And then prior to that, we have a decreasing graph, so still negative derivative values down here, concave down, so it's going to have a negative slope because the second derivative is negative there. What did we just make? That looks a lot like the original graph of f of x, especially if I get rid of all these lines. Right? So what did we just find? That's a very striking result, and this is so important to calculus. What we just found out is that if you're doing an accumulation function on a little f here, so you're doing an accumulation function on this guy, the actual accumulation function, we really don't worry a lot about that. But the striking thing is that the derivative of the accumulation function is the function itself that you are integrating. So our hypothesis that we're going to try to prove is that the derivative is actually the small function that we were integrating. And we see that by the picture. It sure looks a heck of a lot like that's true. So let's see if we can prove that somehow with a picture. So I'm actually not going to use 0 this time. I'm just going to say, let's say we start at some a value. Okay, so let's say we start at some a value right here. And what we're going to do is we're going to integrate up until we get to x. Let's say x is right here. So if we're going to integrate, I'm going to use our vertical lines again because we've been using rectangles to integrate. Many rectangles, right? An infinite number, right? So what we're saying here is our capital F of x is equal to the integral from a to x of f of t dt. So this is my little f function, f of x. And we're using t because we can't use x because we're using that elsewhere in the function. So what we're saying here is that the amount that capital F, the accumulation function, is changing, we want to actually try to show that the derivative, so is capital F prime of x equal to little f of x. And kind of just looking at the picture, that makes a lot of sense to me, because think about how much you're changing at this moment. So if we go just a little bit further, and there's a letter we use for that a lot. Let's say that that value right there is x plus h. And we want to think about that area right there. Because if h is very small, that area is really how the graph is changing at that moment. So what that would mean is the amount that the accumulation function is changing. So delta capital F of x would be equal to the height of this bar, which is little f of x, right? That's the height of that bar, because the height is approximately this guy right here, and then multiplied by some change in x. And that would be the distance between x and x plus h. So you could say that's h, but I'll just use delta x. So this is kind of the first hint, is if you divide both sides by delta x, you have delta f divided by delta x, which is a difference quotient, right? This is a change in the function divided by the change in x. That's like a derivative, is equal to f of x. So again, it makes sense to me that if you're making this infinitely small, that difference between x and x plus h, really all you're doing is adding a line. Let's see if I can change color here to emphasize that. You just have a line right here, and the height of that is f of x. So the amount that the area is changing at that moment is f of x. And this works anywhere. If x is right here, here's our x plus h. That area there has a height right here of f of x. Any point you're at, it doesn't matter where you started. We could have started here, or here, or here, or over here somewhere. It doesn't matter what the function looks like. All that matters is how it's changing at this moment and how high that function is. So this derivative is actually equal to the function that you are integrating. That's crazy. And it kind of makes sense, especially when I think about this point, because if this is the derivative, right? If this guy right here is the derivative of the accumulation function, that means that right here it changes positive to negative, which means that that should be a maximum of the accumulation function. Well, let's think about it. This entire time you've been adding positive area, and then all of a sudden you start taking area away. So yeah, you're going to have an increasing function up until that point, and then at that point you're going to hit a maximum because you're going to start taking area away. So it makes sense to me that this function, this little f of x, is going to be the derivative of the accumulation function. That's just weird. That means you're looking at the derivative every time that you have any function you're accumulating on. That's pretty crazy. So let's see if we can get a little bit more mathy proof. So I'm going to draw that graph again. So we have something like this. Okay. So here's our a value that we're starting to integrate from. And here's our x value. And then here is our x plus h. Okay, so we're integrating up until x, and then to x plus h, this little area right here. So let's just use our limit definition of derivative. So if capital F of x is integral from a to x, f of t dt, then we know that f prime of x, and this is just definition of derivative, it's the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. That's just limit definition of derivative. So let's actually plug these pieces in. So that's the limit as h approaches 0 of integral from a to x plus h, f of t dt, minus the integral from a to x of f of t dt, all divided by h. Well, let's think about these areas. Use some magic technology with colors here. So the integral from a to x plus h, that is everything all the way up to x plus h. Okay? And the integral from a to x, that is just the area up until x. So we stop right there. So if we take the red area and subtract the green area, what are we left with? Just this area right here. So it's the area underneath the curve of little f of x that is between x and x plus h. So really this is just, we're using one of our integral properties. The top of this fraction is just the integral from x to x plus h. That's the only part of the area that's going to be left, because we're taking all the way to x plus h, and then we're subtracting off the part that goes to x. So this is the limit as h approaches 0 of the integral from x to x plus h, f of t dt, divided by h. So let's zoom in on that part. So if we just have the rectangle, and this is actually a curve, so here's our x plus h. We learned about this value in 5.3. So actually, this value, the integral from x to x plus h divided by h is the distance between x and x plus h. This is the average value of the function between x and x plus h. So we learned that that has to be between the minimum and the maximum on that interval. So it's going to be somewhere in there. This is the average value on x to x plus h. Okay, so that is our average value from x to x plus h, and h is turning into 0. So h is turning into 0, which means this value is going to get closer and closer in here. The closer that that value comes in, the more that these two are going to be closer together, these two vertical values. So as x plus h is closer to x, the average value is going to be approaching f of x. So this limit is equal to little f of x. So we've just shown by limit definition that the derivative of the accumulation function is indeed equal to the function that you are integrating. That's crazy. So really all you do is, if you have f of x equal to this accumulation function, if you want the derivative, you just dump the x into the function value right there where the t is. That's weird. So let's actually see what this fundamental theorem of calculus is. So if little f of x is a continuous function, sorry, my handwriting on here isn't great. So little f of x is a continuous function, and we define capital F of x to be equal to the integral from any a value. You can start wherever you want. We saw that in our picture. Doesn't matter where you start, because really all that matters is what happens where you end. So integral from a to x of little f of t dt, then capital F prime of x is equal to little f of x. Okay? So the way that you often see this written is that the derivative d dx of the integral from a to x of f of t dt is equal to f of x. And the reason they like to do this is because then you don't have to bother with this capital F lowercase f thing. So if you want the derivative of an accumulation function, it's equal to the function that you are accumulating on. Pretty cool. So what would a problem look like? Well, I got to be honest, some of them are pretty easy. If we want the derivative of the accumulation function from 3 to x of sine of t dt, this means that you would be integrating or finding the area under sine from 3 to a value. That's pretty hard to do. But the derivative, if you have sine The derivative of that accumulation function, 3 I guess, so pi is like around here somewhere, so 3 would be like here. The derivative of this is just the height of the function. So you take that x, dump it in. It is sine of x. It is that easy, folks. That's it. Next one, if you want to try it yourself, pause the video for a second, see where that x goes, give it a shot. All right, let's see what happens. All you do is dump the x everywhere you see a t. That's it. So it is e to the negative 3x times x squared. That is your derivative. It's that easy. People always ask me on this, wait, don't you have to chain? So my answer is you always have to remember how chaining works, but you're taking the derivative with respect to x, not with respect to t. We are not deriving this function. We're deriving the accumulation function, so the x just gets dumped in. That's like saying, nope, I don't want to do that. I'm not going to try to make it more complicated than it has to be. So here's something a little bit different. This time we have an x squared. So this is where we're going to have to chain. We're going to dump the x squared in, and then we're going to chain on x squared. So this is going to be natural log of x squared. Just leave that part alone. Then you multiply by 2x. So you take the derivative of the function by itself, and then you chain on the x squared. The reason for this, the way I think about this, is let's say that f of x is the integral from 3 to x of ln t dt. So notice it's just an x up here. So let's say that h of x is equal to f of x squared. Okay, so this is a composition of functions. This is something you focused a lot on in pre-calc and in advanced algebra. So if f of x is integral from 3 to x of ln t dt, then f of x squared would be the integral from 3 to x squared ln t dt. That's just a substitution. X squared, x squared. So then if we want h prime, we have to do chain rule because this is a composition of functions. So that means we have to do f prime at x squared. So you leave the x squared alone, but you do the derivative. That's this part. You just take the derivative, leave the x squared alone, and then to chain, we have to multiply by 2x, which is this part right here. So if you have something up top, you just dump it in, and then you multiply by the derivative. Let's try another one like that. So this time we have a much more complicated function. But once again, if you want to pause the video and try this, give it a shot. It's not too bad. All right, let's see how it went. So we're going to take this, we're going to dump it in for t right there. And then we're going to multiply by the derivative of the baby function, which is this whole mess with the x. So the derivative of this will be, I need some parentheses here, I think, tan inverse of x minus ln x plus x all to the 4th power plus 1. Now we're going to multiply by the derivative of the baby. This whole thing is the baby. So the derivative of the baby is 1 over 1 plus x squared. That's the derivative of tangent inverse. Minus 1 over x, that's derivative of natural log. And then plus 1, that's derivative of x. And this is your derivative of the accumulation function because we have to multiply by the derivative of the baby. Crazy. So, I want you guys to try this one. So, once again, pause the video, give it a shot, and see how it goes. So we're looking for the second derivative this time. Alright, let's see how you did. So, first thing we need is f prime of x. Well, that's the derivative of the accumulation function, so we just dump the x right in there. So that is going to be tangent of x. The second derivative of x, then, well, we just take the derivative of tangent, which is secant squared x. And that's your answer. Second derivative of the accumulation function. First one's just tan, because you just dump it in. The second one gives you secant squared. So, this last one that I have here is a little bit more complicated, because we have an x in the bottom and on the top. I want to see if we had one like that before. I think I might have made a mistake, or I might have missed one. No, I didn't. Okay, so a function like this, we have an x on the bottom and the top. Fundamental theorem is only good if you have an x on the top. So the bottom here is going to throw us off a little bit. And before I actually do this one, I want to try one more. I thought I had it in here as an example, but I can't find it. So let's say we wanted to find the derivative of the integral from x to 5 of, I don't know, maybe cosine t dt. So the issue here is, once again, our fundamental theorem is only defined if we have x on the top. So what we're going to do is we're going to use our properties of integrals to get the x on the top. So this would be the derivative, d dx, of negative integral 5 to x cosine t dt. So to get that x on the top, you make this negative because that'll flip the limits. So then it's just going to be negative cosine x. That's it. Because we just dump the x in now, and then that negative sticks around. Because you can pull it out, because it's a derivative, so you can pull the negative out, and then you do the derivative, dump in the x, and the negative still sticks around. So that's going to be important for this one. So the way I think about this is, you've got your function, t to the fourth, so t to the fourth is like kind of a parabola looking thing, and x will be like here, and x squared will be somewhere over here. So many ways to think about this, but I want the area between x and x squared. To get that, I want to introduce a constant somehow. So we could think about this as, if we have integral 0 to x, let's use some different colors here. So the red, we do integral 0 to x, and the green, we'll do integral 0 to x squared. To get the purple area, the area that I want between x and x squared, I can do the green minus the red. The green minus the red. So I'm going to do integral. So I want the derivative of the integral from 0 to x squared of t to the fourth dt minus my red integral. Integral from 0 to x of t to the fourth dt. So this will always work. You can always take the top value, integrate from whatever value you want. I could have started at 1 if I wanted to. I could have done something between them even, but that would be maybe more difficult. So now my derivatives, I just dump in. I'll go back to purple here. So this is going to be x squared to the fourth. On this one we have to chain. So we multiply by 2x. Then we subtract off x to the fourth. Make that look a little prettier. That's x to the eighth times 2x minus x to the fourth, which is 2x to the ninth minus x to the fourth. Now, there are lots of other ways to do this problem. One way that I like to do this is if you say, hey, let's introduce like some c value in here. Okay? It doesn't matter what it is. You can make it like, I don't know, 20, let's say. So you could integrate from x to 20. Let me have the derivative of this. From x to 20, t to the fourth dt. And then we add to it the integral from 20 to x squared. T to the fourth dt. So now we have to use what we talked about up here, where you have the limit on the bottom. We don't want it on the bottom, we want it on the top. So this is d dx negative integral 20 to x, t to the fourth dt, plus integral 20 to x squared, t to the fourth dt. And you can see now, because the value of the constant doesn't matter, we have exactly the same thing we had up here. We just use 0 instead of 20. So now we have 20 to x squared minus 20 to x. That's exactly what we have up here. You'll end up with exactly the same algebra at this point. So a few different ways to do a problem where you have an x in the bottom and the top. So one more type of question they might ask you with this first part of the fundamental theorem. They might say, hey, what is a function that has this derivative? So they might give you anything. In this case, we have 3x squared minus, or times sine x. So if we want this to be the derivative, we can kind of cheat now, because this is difficult. It's a product. I can't really think of something off the top of my head that has that as the derivative, because product rule doesn't work very well like that. But what we can say is, hey, let's define capital F of x as the integral from, pick your favorite number, let's say 5, I've been using 5 a lot, to x of 3t squared sine of t dt. Because what is f prime then? F prime of x, you just dump the x in. It's 3x squared sine of x, which is exactly what they told me they wanted the derivative to be. So it kind of feels like cheating, But this is a totally legit way to define a function. And then the derivative, you just take the x, dump it in, and you are all done. So now we're going to add one more little piece to it. Say, okay, this is the derivative, but I also want 4,0 to be on the function. I want 4,0 to be on the function. Well, on the last problem, if I plugged in 4, f of 4, that would be the integral from 5 to 4 of this function, which would be pretty difficult to do. I have no idea how to find that area. Okay, I don't know how to do this. But if I know that when I plug in 4, I want it to give me 0, that I can deal with. Because there's one thing I know. So let's leave the bottom blank for a second. We're going to go up to x, 3t squared sine of t dt. Whatever the bottom value is, when I plug in 4 up here, I need it to give me 0. Well, there's one thing we know about integral properties. If I integrate from 4 to 4, that's going to give me 0 for any integral that you have. So now we have that f of 4 will be the integral from 4 to 4. Doesn't matter what this function is. 3t squared sine of t dt is fine. That's going to give me 0. So I've satisfied the only condition that they gave me. When I plug in 4, I get out 0. One more. What if I want 4, 2 on the function? Well, messing with that bottom limit is not very useful. So I'll put in my function here again. If I change this bottom limit to anything else, if I try to make this integral be 2 when I plug in 4, like maybe I say, well, maybe if this is like 3.6 and I plug in 4 at the top, maybe I'll get out 2. That is not going to work because you'd be messing with this value all day trying to get it to be 2. But watch this, and this is where it really feels like you're cheating. I'm going to leave this as a 4. Now when I integrate from 4 to 4, it'll give me 0. All I have to do to get that 2 to happen, add 2 on the outside. I know it seems cheap, but that's all it is. Now if you take the derivative of this, this is a constant, so it disappears. When you take the derivative, you'll just dump the x in. So f prime will still be 3x squared sine x. So that's true. And when you plug in 4, 4 to 4 gives you nothing, and you add 2, so 4, 2 is on that graph. Crazy. So that's all I've got for you on this one. If you need to go back and watch any part of this, it's a very important lesson, so make sure you understand it, especially the proof and how that average value works. And make sure you move on and watch 5.4b for the second part of the fundamental theorem. I love you guys. Have a great day.